The intersection of quantum physics and consciousness is one of the most profound frontiers of modern thought. As we seek to understand how mind and matter intertwine, theories like the many worlds interpretation and the phenomenon of quantum entanglement challenge our classical intuitions. In this chapter we explore how frozen time theory, which posits that time is a static collection of moments through which consciousness navigates, relates to these quantum ideas. By comparing frozen time to MWI and by reinterpreting entanglement through a timeless lens, we uncover a fresh perspective on reality's deepest structures. Proposed by Hugh Everett III in 1957, the many worlds interpretation of quantum mechanics offers a radical solution to the measurement problem. According to MWI, the wave function never collapses. Instead, every possible outcome of a quantum measurement actually occurs, each in its own branch of the universe. When a quantum event happens, say an electron's spin is measured, the universe splits, and each outcome is realized in a separate non-communicating world. Key features of MWI include branching universes. Every quantum measurement generates a branching structure of universes, each containing a different outcome. Observer splitting. The observer herself splits along with the universe, experiencing each possible outcome in a different branch. No collapse. The wave function evolves deterministically without any collapse triggered by observation. Frozen time theory proposes a fundamentally different approach. Rather than imagining a continuous splitting of the universe into parallel realities, it posits that all possible moments of time already exist as static frames in a timeless block. Consciousness does not split but instead selects or navigates among these frames, giving the subjective impression of motion and causality. Key distinctions between frozen time and MWI. Single consciousness navigation. Unlike MWI's splitting observer, frozen time theory maintains a single, unified consciousness that experiences one moment at a time. There is no literal splitting of the self into multiple versions, no branching worlds. All possible outcomes exist within the block universe, but they are potential experiences rather than separate physical worlds. Collapse as selection. Where MWI denies collapse, frozen time theory reinterprets collapse as a metaphysical selection, consciousness choosing a particular frame from the sea of possibilities. Economy of ontology. Frozen time theory offers a more parsimonious model, avoiding the proliferation of infinite physical worlds inherent in MWI. In this view, the experience of decision-making emerges from consciousness navigating a block of potential moments, each consistent with different quantum possibilities, without invoking branching universes or multiple selves. Quantum entanglement is a cornerstone of quantum theory, first described by Einstein, Podolsky, and Rosen in 1935. When two or more particles become entangled, their properties remain correlated regardless of the distance separating them. A measurement on one particle instantly determines the outcome of the other, a phenomenon Einstein famously called spooky action at a distance. In standard quantum mechanics, non-local correlations. Entangled particles share information instantaneously, though no faster than light signal is transmitted in a relativistic sense. Measurement collapse. When one particle is measured, the wave function collapses, and the entangled partner's state is instantly determined. In frozen time theory, entanglement takes on a new meaning within the block universe framework. Rather than requiring a physical influence propagating between particles, entanglement reflects pre-existing correlations between static frames of reality. Key insights. Entanglement as pre-linked frames. Entangled states correspond to frames that are inherently correlated within the block universe. These correlations exist timelessly, no signal needs to travel between them, no action at a distance. Since all frames coexist timelessly, no causal influence is required. The measurement simply reveals a consistent outcome in the observer's navigational path. Consciousness as selector. The act of measurement is not a physical collapse but a selection of a particular frame by consciousness, consistent with the underlying entangled structure. Holistic reality. Entanglement exemplifies the deep interconnectedness of all moments within the block universe, a hallmark of quantum non-locality reframed as timeless unity. This approach aligns with certain holistic interpretations of quantum mechanics, such as David Bohm's implicate order, yet retains a unique emphasis on consciousness as the navigator through a pre-existing landscape of possibilities. In comparing frozen time theory to the many worlds interpretation and quantum entanglement, we see how quantum mechanics can enrich our understanding of consciousness and perception. MWI versus frozen time. MWI multiplies physical worlds to account for all possibilities. Frozen time preserves all possibilities within a single block, with consciousness navigating between them. This reframes the collapse as a metaphysical rather than physical event. Entanglement in frozen time. Entanglement reveals pre-existing correlations between static frames. Measurement is a conscious selection of one of these consistent frames. No physical influence is needed. Correlations are timeless. By integrating these insights, frozen time theory offers a holistic perspective on the interplay between quantum mechanics, consciousness, and the nature of reality. It invites us to consider that our experience of motion, causality, and choice arises not from a dynamic unfolding but from our consciousness navigating a static, yet richly interconnected tapestry of possibilities.